Thank you for joining us for our water webinar, Ask ISCO, How to Measure Flow in Hazardous Locations. If you have any questions during the webinar, please utilize the chat or Q&A functions within Zoom. All questions will be answered at the end. This webinar will be recorded and a video will be made available in the next few days. Our presenter today is Rick Dye, Business Development Manager, Flowmeters. With that, I'll turn it over to Rick.
Thank you, Sharon. We'll go ahead and get started here. Sharon said my name is Rick Dye. I'm a Business Development Manager for Flowmeter Products with Teledyne ISCO Water Platform. Today we're going to talk about some pretty exciting stuff, or at least I like to think it is, measuring flow in some difficult applications, and we're seeing more and more hazardous rated locations. So let's go ahead and I'm going to try to go through this and give you a quick overview of why we measure flow. A lot of ionized studies, or in Europe they're called flow surveys, enforcement requirements, industrial pretreatment. We have billing applications, custody transfer, which are basically cities discharging to other wastewater treatment plants. Some examples of that would be Atlanta, Phoenix, Milwaukee, Boston, Denver, and really the list goes on and on. For those of you that have not been to the ISCO facility, this is the flow measurement lab. We do a lot with development design work here, and so this thing has been very, very useful for us. We can simulate a lot of hydraulic conditions, so not only in design and development, but as we continue to evolve and improve the existing products we have out. And the LaserFlow that we're going to be talking about is no exception to that. We've learned a lot since we released it in 2013, and a lot of these improvements have been made using our flow lab. I'll say not many people, if anybody, has a facility quite like that. So let's talk about some of the typical flow meters or monitors that you might have been used to or familiar with in the past. The one on the left is a Flowmeter 4200 series. Has a built-in printer and so on, keypad, display. One on the right is a flow logger or monitor. It is a wake up, take a snapshot of what's going on, and goes back to sleep. These have been changed and to some of the updated equipment. I'm going to go through a little bit of that with you. But when you're looking at your equipment options, you need to look at, do you have AC or DC power? And depending on which one you have a couple choices for your meter. One would be the signature flow meter. That can be both portable or permanent. The other would be a 2160 or blue box unit. A lot of people are familiar with the 2150s out there. Uses the same concept with the 2100 series platform, and I'll talk about that a little bit. But the blue box unit is typically battery powered, wakes up, takes a reading, goes back to sleep. They're more waterproof and designed to be in the manhole environment. The one on the left, the signature, is more of what we call a smart device. It's very flexible. Technically, it can handle 9 different smart sensors. All of our sensors coming out now will be smart. What I mean by that is you plug it into a signature flow meter, you can scan for it and it says, oh, I'm a laser, I'm an ultrasonic, bubbler, whatever. So it can take a lot of different inputs, not only from ISCO equipment, but it can take inputs from other non-ISCO devices. So if you have something that has an SDI-12 output or Modbus output, we can take those, we can store them in the signature. We can also transmit that data via cell phone. We can send it out, analog output, Modbus, Ethernet, and so on. So a lot of flexibility with the signature flow meter. 2150, this one has been around since '99. We sell a lot of these, and these are really the workhorse of the industry. They're designed for more temporary monitoring, but they use a standard area velocity type sensor. And area velocity, let's talk about that. Q is your flow, is equal to the area, which is used or calculated using some level measurement technique. We typically use a pressure sensor on a 2100, but you can also use ultrasonic. We use ultrasonic on the laser. Once we know the area, we need to know the velocity. V is our velocity component. It's a Doppler technology or technique. We can either do a contact, which means I have a sensor on a ring in the water, or non-contact in the case of the laser. So we'll talk a little bit about both of those. So what does this thing actually do? To give you kind of a better idea, you have a sensor typically that's on a ring that's in a pipe. So you know the pipe dimensions, you plug that into the meter. I have a 12-inch pipe. It measures the level using a pressure sensor, and then it transmits a Doppler signal out the nose to measure the speed of the water or the velocity. So pretty good little artist rendition of how that thing works. Everybody's fairly similar in how they take that measurement. Okay, so that's a real brief overview of a contact sensor. Let's talk about the non-contact now. Why do you go to non-contact? Maintenance obviously is a big one. Safety is a big one. And not all product is going to fit every application. So we have a bunch of different types of technologies that we've had in the past. We've since streamlined some of those down and more focused on a product that's going to fit most of your applications. So this one is the LaserFlow. The LaserFlow is not perfect in every application, but I will tell you from my experience in the industry, this is the closest I've ever seen to a one-shot-fits-all kind of technology. But let's explain how this works. Even though this is a non-EX laser, the technique and the way we measure is very similar to the EX. So I'm going to go through this one and explain how we do what we do with the laser. So we have an ultrasonic sensor that's in the back of the laser itself, transmits, reflects off of the internal molded housing, knows where the water is. Once it knows where the water is, it focuses the laser below the surface of the water. This is a key point and something that you need to be aware of because we are the only ones currently that do the below surface velocity measurement. We have a patent on that. There are a lot of radar units out there that measure surface velocity, but we are the only ones that measure the below the surface water velocity. So that's key. Before we get into that, let's talk about the ultrasonic and what we do with our level measurement. One thing we looked at when we designed it was some of the limitations of what was currently out there. One of them was the ultrasonic. What we did with ours is we mounted it at an angle in the back of the sensor. The reason we did that is so the moisture will not accumulate on the sensor, whether it's just humidity in the environment or if it's submerged. We have a molded deflector, 22.5 degree deflector, and that will go ahead and actually reflect that ultrasonic signal down into the water. What we did too with the deadband, every ultrasonic sensor typically has a 12-inch deadband, not all, but most, and we took that into account on the design. So now that's taken into the measurement. So we have virtually zero deadband ultrasonic built into it. The water will go all the way up to the laser bottom before it will quit reading the level. So good design there. We think we made some pretty good improvements. We have a 0 to 10 foot range, so it can be 10 foot away from the lowest water level. All right, so we did a pretty good job, we think, on the ultrasonic level. It's been very reliable and accurate. But now let's talk about the laser and what we do with that. So a laser pointer has a constant focal point, so that's why laser pointer will just shine on pretty much infinity is what I meant. But anyway, so the focal point is the key part with the laser. So we actually know where the water is, but what we'll do is we will actually move the laser and focus the laser below the surface. So we change where the laser is, we know where the water is, and we know where we want to focus. Like any Doppler device, we know the frequency we're transmitting, we know the return frequency to calculate the Doppler shift. So let's look at a front view, side view of the laser. We have an ultrasonic. Once we know where the water is, we know where we want to focus. If you stuck your hand under the laser, you'll see the dot size of a coin. Where it hits the water, it should be a very tight focal point. We do that again below the surface. This area is known as the point of convergence or converging section. That's where we're getting our maximum signal energy reflected back to the laser itself. Key thing with this design is that we take 5,000 velocity readings and we do it all in about 2 seconds. Those of you that were early adopters of the laser back in 2013, that unit took about 45 seconds. So we made some improvements again with the design, and now it does it all in a very short amount of time. So that helps a lot with pump station type applications and things where you have rapidly changing flows. So it's been very a good improvement. Okay, The key thing with the laser, and one thing I like is when I get a reading, I want to know that that reading is correct. We are one of the few companies that probably push a lot of the diagnostic capability of what the laser is doing, or all of our meters are doing. And if you look at this, what you'll see is we have a return frequency spectrum. The bottom frequency is the speed of the water. The faster, it's more to the right, and then the slower the velocity, more to the left. We take that velocity reading, we scan it 10,000 or 5,000 times. The more that agree on the return, the better that Doppler shift looks, or that spectrum looks. When we look at this diagnostic, I can tell remotely, I can tell after the fact, or even when you download data, if that laser was working right. So now I have confidence in the velocity reading that I'm getting. Give you another better look at what we've done is we made some improvements over the first laser where we took out some of the noise source. And what that means to you is that the laser now is a very, very clean signal. We have a strong signal, and the bottom level there is the noise floor. The magic behind any device like this is you want to have a strong signal-to-noise ratio. And so when this water level slows down, or the water velocity slows down, it will shift to the left. When you get closer to zero, that's where typical technologies are going to struggle to read because you get into the noise floor. With the laser, it is so clean that we really have no noise, and it will read at a very, very slow velocity. This reading is stored as something we call Doppler Power, and it is stored in the memory of the meter. Every time it takes a reading, it does one of these. When you're post-QCing data or looking at data, you can graph that. Doppler power number needs to be greater than 1,000. So now we have a good way of getting for lack of a better term, an MRI of what that laser sees, and then graphically we can lay it out there and see what our Doppler power is with the data set when we're viewing data. So very, very powerful technique and way to verify that the meter is reading correctly. Okay, so accuracy, we have a ton of accuracy comparisons out there. We are an M-Cert, which is more of a European thing, class 2. Our current published specs are 4% of reading. That includes the Laser EX. We have a lot of third-party test results. One was the Irrigation Training and Research Facility in Cal Poly, San Luis Obispo, out in California, a well-respected research center out there. They did some testing, found that the absolute error on the laser was about 1.8%. We also did some testing on the East Coast, which is a place called Alden Research Lab, another very well-respected facility out on the East Coast. And they ran it in a 30-inch pipe, and they found it to be within about 2.5%, 2.7%. So we have, again, tons of data, field data tests, as well as lab data to support the accuracy of the laser. So some of the typical applications. When we developed the laser, we designed it for collection system monitoring. We looked at large pipes initially. We know people don't want to obviously get in the water, and when it's large, it's very, very dangerous. Working with some people in Phoenix, Arizona, they have 84-inch pipes, and that water is moving 6, 7, 8 feet per second. You don't want to get into that flow. But we also found that the laser is very useful in small pipes. We define small pipes as anything less than 36. That's probably a little high. But we found now that we're using lasers more and more in pipes that are 6, 8-inch pipes, and a lot of industrial monitoring because of the ability for it to read very, very low flow and very rapid changing flows. Okay, so some of the difficult applications that we run into: high velocity where you have very low level, steep slope pipes. I've seen more steep slope pipes than I ever dreamed were even out there in the industry. So a lot of these were just not measured because there was no way to measure them. When you get into low level raw water velocity, raw wastewater, and typically you're going to have levels less than 1 inch. Any AV sensor, standard area velocity, needs at least 1 inch in order to be able to get a velocity reading. Slow velocity, as I mentioned, is a very, very challenging thing. Anything less than about 1/2 foot per second is going to be difficult at best. Residential collection systems is where you'll find those a lot of times as well. You have very slow, clean water, a lot of times wastewater effluent. If the plant's working correctly, which we all hope they are, your effluent is going to be very clean. We're also finding applications where they want to measure the UV disinfection channels or chlorine contact chambers, and the laser is able to actually measure that type of water. Drinking water influent, so more and more raw water coming in, they want to measure that. Storm water, that's a big one now. Why? Because wide fluctuations in your flow conditions make it very difficult. And a lot of times you have irregular shaped channels. So, you know, with a stormwater application, you don't want cables in the water and things like that that's going to catch debris, tree branches, and so on, and just get ripped out. So we see a lot of those types of applications. So let's look at some pictures here. This is a low-level high velocity. This is Duluth, Minnesota. It's coming off the bluff, and that water is moving through there. They've tried to measure that flow, and we're unsuccessful with the traditional area velocity. You just couldn't put anything in there. The laser is spec'd at a ½ an inch minimum for velocity, and we can read up to 15 feet per second for maximum velocity. This is what the sensor looked like when they went ahead and installed it. Stainless steel mounting brackets, easily installed. There's 2 bolts that hold that bracket on there, and the sensor just slides right in, locks in place. It knows, the laser has a built-in accelerometer like your cell phone, so it knows the X-Y axis. It knows if it's surcharged, went underwater, if something shifted, it will tell you that as well. So very intelligent design as far as knowing where that sensor is. The Y-axis, which is the 45-degree angle, will tell you, basically you need that for the accurate velocity measurement. If you don't get it perfectly installed or it changes a little bit, the laser will mathematically compensate based on that accelerometer. The laser can be mounted either pointing into the flow or away from the flow. We don't care which direction you mount it. It can also measure bidirectional flow or velocity. So here's one that was a site in Canada. They had a pretty challenging, to say the least, application. The water velocity in this point where I've selected right there was 13.02 feet per second. So incredible velocity, very, very difficult, and nothing's going to have a good time measuring that at only 7 inches deep. 7 inches deep, 13 feet per second is an incredible challenging application. So some of the slow velocity applications, this is more and more we're seeing these. What is slow velocity? Typically anything, again, below ½ foot per second. We will see a lot of applications where we're even far below that. Why is that so challenging? Because most area velocity sensors can't pick out the signal from the noise. And again, you'll see that more prevalent in clean water applications. Why will the laser work? Well, as I mentioned, the signal-to-noise ratio is exceptional, and that's what it's all about, really, is picking out what is real and what's not, and being able to calculate that. Because of that, we can read really very slow velocity, very low velocity. There are some technologies out there that can read in the same area as the laser, but not many, so this is another very good feature behind it. We specify currently ½ foot per second. So this will give you a little better idea what more of a temp mount. There's a cross piece they use. It's not ours, but it was one that was in there, and they just mounted that across it. You can see the laser dot on the water there, but you can also see that the water is like glass. That's a challenge for any non-subsurface measurement, because as you get wider and wider channels, even with higher velocity, the surface of the water can be like glass, and that makes it difficult for a non-laser unit to be able to read that velocity. The laser, we're going below it, so we were able to pick up that velocity very accurately. Here's an example of a site where we measured down to 0.39 feet per second, and you'll see that dotted line there on the second pane. That's our specified velocity. So our spec is ½ foot per second, and we were reading way down below that. I will tell you that we have applications where we're reading down in the 0.2 foot per second range. So as long as you have something in the water, entrained air, some sort of particle, we can typically pick up a very, very slow velocity. Okay, so I included some of these pictures to give you some application ideas. of what you can do to install one of these. Really all we need is a small opening in the top of a pipe. This happens to be the ISCO Flow Lab. You'll see we have a bunch of these notched out. So depending on how high up the laser is in our testing, we hit the right opening. But really you only need an area that's about 4 inches by maybe 10 to 12 inches long. This is a good shot of the laser actually hitting the water itself. Here's one where a customer had an industrial monitoring location, pipe going through the manhole. All they had to do was just cut open that top, and now the ultrasonic is going to read right below roughly the handle, and the laser is going to focus into that pipe itself. This is ideal because you have no transitions going into the manhole, no transitions into the invert, which can cause you some problems. So ideally, if you can do this, you're going to be very accurate, and no maintenance. You're going to be able to read all the way through almost full pipe very accurately. Again, a lot of industrial monitoring applications like this. There's a laser on the water, so you can see it hitting. All right, so this is another one to give you a little bit of an example of where they adapted to their application. This is a shrimp factory in Louisiana. They needed to measure flow coming out of that PVC pipe. All they did was cut an opening in the top and mounted it a little bit away from the end so they're not affected by the drawdown. And now they're able to measure the level and the velocity and get accurate measurement from a very challenging, difficult application. This is one that was in Las Vegas. You'll notice they cut out some of the pipe to be able to get at that, but putting something in that flow, and you can see it's high velocity, it was going to be very, very difficult for them. So the laser's mounted right over it. They use some rebar strut stuff in order to get better support, and now they have a nice application, a good install, and didn't need a lot of room to do it. So it was a good install for them. This is give you a better idea how these are mounted. That's a stainless steel mount. You'll see they're on the wall. There's 2 bolts that hold that bracket on there. And we're measuring the effluent of a wastewater discharge. So did a very good job there. This is one that I wanted to show you. Hopefully you can see the video. This is one where I have and you can see all the entrained air on the flow itself. A lot of swirling, horrible hydraulics. So what they did was they said, will the laser work? Well, we didn't really know, to be honest. So we said, go ahead and put one in. Let's see what it does. And that's what it looks like. So they just easily installed that. That channel is probably 2 foot wide. And you can see, again, all the air bubbles on that. When I got the data, I wasn't overly impressed with it because notice what appeared to be dropouts in velocity. When I looked at that, these were not actually showing it going to 0. They were showing it going down to a very low velocity. So I grabbed a diagnostic from that site itself. So you'll notice the ones I showed you before are nice, pretty peaks. This is not quite so nice and pretty. But what's interesting about it is you'll see a couple peaks here. One is a very low frequency, low velocity peak, which means that's very slow velocity, which was the entrained air or the air bubbles on top of the water itself and the foam. This one is what they really wanted to read, which is the discharge, the speed of the water, the real velocity. So what I was able to do was I was able to make some adjustments to the meter and say, ignore everything left of X. So I can kind of tweak and fine tune the laser to ignore that stuff on the left. Not that you ever have to do that, but this is one of those extreme applications where they couldn't get anything else to work. The red line is where I made those changes, and you'll notice to the right, everything now looks really, really good. This saved the customer a lot of money because they were going to have to do a lot of redesign, construction, and so on. So making some small changes based on what the laser's telling you is a really, really good thing for them. This is one where I just did a temporary test to find out how clean of water we could read. This is the wastewater plant in Lincoln, Nebraska. It's very, very clean water coming out of there. And the laser was able to actually measure that very accurately and quite well. This was a high velocity channel down in Kansas. This was not so fun to read, but we could see that in the diagnostics, we were going to have a difficult, if impossible, time measuring that. But with diagnostics, it was able to tell us, hey, we're going to have some problems here. But they were able to do some things. We got some stuff to work. And what they did was we went ahead, we mounted it. It was kind of a neat install because all he did was cut open a small opening in the top, mounted the laser right on there, and away we go. So easy to install. You don't always have to use the mounts that we have, but that's one way to do it. Okay, so here's another challenge we had. Initially in the laser, we read the level right below it, and we focused the laser based on where the level was being read. This site was in Istanbul, Turkey. I was actually at the site, and you'll notice that drawdown, there was no way they were going to be able to use the standard laser. So what we did is we made some modifications to the laser to use what we call a remote ultrasonic. And the way that works is that sensor, instead of ordering it with the built-in, we ordered it with a remote. What that does is that mounts up in the pipe, or it can mount outside the pipe, but in this case, we mount it inside the pipe. We mount it horizontally. It reflects off a deflector plate mounting bracket. Now we are measuring the level in the exact same spot that we're measuring the velocity and shooting the laser. So we're able to adapt to those types of applications that we were not able to before. You'll see that picture on the left. That was a site, CSO site in Iowa. This is one that was in Washington State, and you can see they had a little bit of a drawdown coming into that pit. We see that quite often in a lot of applications. So they were going to struggle to get a good reading out of that. So the ultrasonic is mounted right up in there, and now the laser is able to read in a more defined and accurate way. This is a CSO Outfall, and we see a lot of these. You'll notice a small drop, about 2 inches from the pipe coming into the rectangular channel, and mounting the remote ultra up in that pipe now allows us to do a couple things. Instead of measuring below the pipe, we now know where we need to measure, and we're focusing in the right spot. So we're able to read, and again, CSOs, we see a lot of those, which are combined sewer overflows, and these are typically in the older cities in the U.S. and worldwide, but these are, again, very challenging because you put anything in there, and typically when you have a rain event, that water's coming through and it'll tear out whatever's in there. All right, so here's another application we're seeing more and more of. This one really isn't as bad as a lot that I've seen, but a lot of times the water will come into a manhole and it'll make a 90-degree turn, and we were not able to read those very well because the ultrasonic sometimes would hit the bench or the floor and not the water. So what we're able to do is we're able to actually use the remote ultra, mount it over the pipe coming, or the water coming in, and then the laser can shoot into that. Now we don't care what's going on. So you can do it with, you can measure with really a very few straight runs in some cases. Now people ask me that all the time, what do you recommend? And we always say like 5 up and 2 down. Give it the best chance you can. It's not a miracle cure, but the thing will measure some challenging applications like that. Okay, so here's some river applications. You know, why are they challenging? Obviously, you go from low flow to, you know, raging rapids when you have some storm events. Sensor cables, just like stormwater lines, that you have to deal with. And you are going to probably have some inaccurate velocity measurement due to technologies. And what I mean by that is if you have a river and you're working with 2 inches of water on normal dry weather flow, when it rains it goes to 10 feet, a standard area velocity is going to lose accuracy as you get deeper. Conversely, if you have a high-level, high-accuracy device, it may not even see the low end. So very challenging for that. So the laser is able to handle that because we can read very low flow and very slow flow. A lot of times that water level or the water flow will slow way down. And we can adapt to the high flow rate, so we don't care really what it's doing, low or high. And obvious benefit is nothing is in the water. We're not going to have cables that are going to be torn out and anything like that. It makes it easy to install. And again, we're going to be accurate through the entire range. So this is a site that we did some testing on, which was pretty interesting because this is normally almost a dry channel, but when that water, when they get rain, everything dumps into this. And so You don't want anything in the flow. They mounted it easily off of a bridge, so pretty good install. You'll notice on top of that one, there is a sunshade. So if you have it outside, you'll probably want a sunshade because of the ultrasonic level, not the velocity, but the ultrasonic doesn't want to have or get heated up by the sun. So good way to measure this, about the only way you can measure that. Large channels, more and more of these. The good thing about this channel is it looks well defined. It's the effluent of a wastewater plant. And so if you measure off to the side, you're probably going to be fairly close to being where you need to be. Perfect world, you're right in the middle of that flow. You can mount multiple lasers in a channel like this. So we can mount technically up to 9 lasers on one signature flow meter. Realistically, you can do 3 comfortably. But in some cases, in the UK, they're doing 3 on channels that are over 5 feet wide. Nice mount, or thing about this mount is they can swing that mount back if they ever needed to get it out of there or do whatever. So they have a good sturdy mount. It's also has stainless steel suspension cables. Here's a channel in California. So if you're from California, you've probably seen these. Normal flow is very low, so they have a notch in their wide rectangular channel. And this is where they were trying to measure before. They had kind of a makeshift flume that wasn't accurate, so they're able to use the laser to measure the water coming into that. But the neat thing about all of our meters is we can do level to area data points as well. So we can measure that flow in that rectangular part, and then when it goes and exceeds that and flows through the entire channel, we're able to measure accurately the flow, or as accurate as you can be. Now the laser is not going to see that entire width of that channel, so I want to make that clear. But it sees roughly a loaf of bread in the flow. Okay, so that's kind of how the laser works. Let me show you what do we do when it goes underwater. I'll apologize for you that are getting ready for lunch. This is Detroit, Michigan, and it's a big channel they have, 14 foot, and you notice the log cable on that. So the laser can handle submergence. It will handle 6 feet for 72 hours. We have had them in a lot worse condition or a lot worse applications than that. Most of the time, only thing you have to do is maybe clean the stuff that's hanging off the nose. Okay, so when we look at what kind of maintenance is involved with the laser, you have your level calibration. Really, you have a non-drifting ultrasonic, so you only periodically need to check that. You have a velocity verification using the diagnostic. So you really don't have to do a whole lot with any of the calibrations of either device. Yes, you can periodically do a manual profile and check it with a handheld device, but I will tell you that those are pretty old, and that technology's been around for a long time. So they're good technologies, but I would bet on the laser over that, but it certainly will give you a second opinion and give you a little more confidence in the reading. Okay, and again, the graphic with the Doppler power and some of the reporting capabilities that we have. So if you look at this one, this channel, you'll notice the level on the top was going along. You had the velocity in the middle, and the level went up, the velocity shot up, and all of a sudden our velocity went down to flatline, okay? So you'll notice the third pane is called Doppler power. Again, a measure of the quality of the velocity reading that we're getting back. In the top right, you'll see Doppler power 5867. We need 1,000 Doppler power to consider it good. So here's a good indicator. Hey, we got something going on there. Something went up, it's probably underwater, or it may have came loose from the mount, who knows, but you now can remotely determine if you have that. Okay, so what do we do when we go underwater? We have a sensor that mounts on the bottom, and it's similar to a 2150, although it's called a Model 350. It's an area velocity sensor. So it mounts on the bottom. It uses a pressure sensor built into it to measure the amount of submergence in that channel. We use a continuous wave Doppler technique to measure the velocity. What's nice about this is with these types of continuous wave sensors, if it's mounted at the bottom of a pipe, as you exceed 2 feet of depth and deeper, your velocity accuracy will tend to decline. Us and everybody in the industry will have the same issue unless you calibrate it at a different level. The neat thing about this one, it's mounted upside down. The nose of the laser is typically mounted at the crown of the pipe. So now we are reading a higher velocity because we are able to see where that peak velocity is. So while this is not a perfect flow condition, the laser, coupled with the AV sensor, does a pretty good job on that. Okay, so here's a couple stormwater pictures. This one, for obvious reasons, in LA, they didn't want anything out exposed. It was probably not going to stay there very long. So in stormwater applications, it's easy to mount these things. So here's a couple guys installing this. They actually use C-clamps and just clamp the mount to the top of the pipe. So that worked pretty well for them. This kind of gives you an idea of what that looks like both in and out of the pipe. So here's a site that I call extreme stormwater, and the reason for that is they're working with about a 48-inch pipe in no flow. I mean, very, very low level and very clean water. You'll see the laser on the water itself. We were able to measure this velocity in this location, which is incredible that we can measure something that low. So here's an example of what we were dealing with. We're less than an inch deep, 0.88 inches, and our velocity is 1/4 of a foot per second. And we're nailing that all day long. So it's pretty amazing what it's able to do. Okay, that is the laser. I'm going to talk about the LaserFlow Ex now and kind of give you some ideas. What is NFPA, and what is Zone 0, Class 1, Division 1, and kind of some of the customer needs and why we developed this. But it uses the same technique, same technology as the standard laser. There are a few differences, and I'll explain those. But why did we come out with the Laser EX? Hazardous rating. So every sewer technically is rated NPF 820, and that means it's a hazardous location. They are technically rated Class 1 Division 1. So as the newer generation comes along, we have consultants that are typically going to specify Class 1 Div 1 because they want to be safe. In Europe, they do an ATEX Category 1G Zone 0, so that's international standard. We have both of those. IEC EX rating, international. And really the laser is the only one that provides this rating with the kind of performance and accuracy of the laser. So we are Class 1 Division 1. There are Class 1 Division 2 units out there, but that doesn't technically meet the rating. Okay, so let's talk a little bit about some of the differences. The laser standard unit that you buy right now will be blue. There's no other feature changes to it. It's compatible with both with the 2160, which is the laser module, the blue box, as well as the signature itself. The LaserFlow EX, you can see that that's a little bit different. There's a little bit of a mount on the back, and there is the ultrasonic. It has to be mounted slightly different on that unit to meet the rating. But it will be a black sensor. It has conductive fibers in it, which is one of the reasons that we use that. It has a large intrinsic safe label on the side to identify that it is an EX unit. And again, the 310 ultrasonic is mounted on the back. One difference is the standard laser can measure 15 velocity points. So it can go horizontal 5 and vertical 3. The EX, due to the power requirement, is limited to 3 in the middle, in the center. So it's going to look something like this. Knows where the water is, knows where it wants to focus. So if your hydraulics are relatively uniform, you're going to have no problems using the EX. If you have some bizarre hydraulics, you may have to find a better location. But this is known as a multi-point, multi-depth velocity method. This is a typical velocity profile, and just kind of give you an idea of what those look like. But what we're looking for is right below the surface, or below the surface at multiple points to find the peak velocity. Okay, so intrinsic safe environment. That applies to anything in collection systems, combined sewers, storm sewers, pump stations, wastewater treatment plants, sludge handling, chemical handling facilities, and treatment facilities. So we are now able to work in a lot more applications than we were prior to having the EX. A lot of wastewater plants. Influent to the plant is almost always a hazardous location. So while we don't see this 100% everywhere, it is gaining in requirement. So some of the places that do require this, Canada, the collection system, all over they require that. Australia, Singapore, UK, Germany, etc. over in international. Massachusetts, the MWRA, Influent Wastewater Plant requires it. New York DEP, Phoenix, Milwaukee, Seattle, and the list just keeps growing and growing. So a lot more requirements like that. So again, we get asked, how well do these two compare? And we did a lot of testing comparing. Again, I call it dueling laser. You have a non-EX and an EX laser head-to-head. This is what the data look like from those. So you'll see the standard laser, the top level is, or the top pane is level. Second is velocity. The third is flow rate. So you can see that they're almost mirror image of each other. So we've seen no difference really in the accuracy between the two. So let's just go ahead and conclude this, and I'll open it up for questions, give you a little bit of time for that. LaserFlow is amazing. Again, I've been doing this for 34 years. The reputation of what it's capable of doing and the market share that we're capturing has been a fun ride and incredible. Provides a complete solution really for your contact or your non-contact needs. So now we can provide the signature meter, we can do the laser 2160 module. So we give you really everything you could hopefully need at this point. And you have accurate data with no risk, so it's minimize the risk of explosive atmospheres, and you're not paying a heck of a lot more upfront cost for that. So you put up a little bit more money up front, but you have no maintenance, no people going in there, and no risk of explosive atmospheres. So now we'll go ahead and we'll open this up for some questions. So let's see, one of them was, okay, if I have a 2160 laser module, can I update or upgrade it to a laser EX? And the answer to that is yes, you can. What you need to do though is you will need to get the barrier. There's a barrier, the intrinsic barrier that goes between the laser EX and the laser module. So in that case, the 2160 blue box is not rated, so that would have to be out of the environment, and then the barrier would be connected to it, and then it would run into the hazardous location. So you would not need to do anything to the module, but you would need to replace the laser with a laser EX, and you could, and again, put the barrier in there. So you can definitely do that as well. Okay, here's a question. Is there a difference in the type of power or energy from the laser EX versus the standard laser? And that's a good question. I've been asked that a few times. People want to know, if my water level goes up, do I transmit more power? The energy or the power that the laser transmits is the same regardless of the depth, and it's the same regardless of the laser itself, or the EX or standard laser. One thing that I should point out is the laser EX will read, it takes a little longer to get a reading, and I'm talking seconds longer, so it's not a lot, but it will take a slightly longer because of the power limitations. Okay, so another question, accuracy difference. Is there a difference in the accuracy of the laser? The answer to that is no. They're both rated at 4% accuracy. Having said that, if you do have a kind of bizarre hydraulics, the non-EX will give you more samples or more points to read. So it may help you read slightly better in very, very difficult applications. But in a normal application, and we tested initial lasers using the single point in the middle, they tested extremely well. So in most cases, you will see no difference at all with the accuracy of the two. Okay, laser mount install. Can I mount my laser with a temporary mount because I don't want to drill holes and the customer has robust pipe? Is that right, Rob? But anyway, so yeah, the answer to that is we do have a temporary mount, and what that is a hydraulic kind of jack system. You go in there, you put your mounting bracket on it, and you can jack it out to hold it in place without drilling holes. Laser will mount on that. With the XY axis or the accelerometer from above, you're able to tell if you have any problems with the mount. It'll tell you your X angle, Y angle. You get that set up and away you go. Those work really well in temporary applications. If you're going to use it permanent for long periods of time, you probably don't want to go that route. You're going to want to just put a couple holes in there and mount that, or find another method. We have a lot of people that use some sort of rebar or all thread and things like that, where they're able to use a different way to mount that. So you don't have to necessarily use RU channel bracket, but you certainly can. So anyway, good question there. Okay, communications. I didn't talk about communications on this one due to time, but we do have cellular communications, and those will allow you to do a couple things. You can push data to a central database, or you can pull data. What I mean by pull data is you can call the site up, download the data. It's kind of the old-fashioned way. For those of you that have FlowLink Pro, you can have it push data to FlowLink Pro, to your server, and we have a lot of customers that do that. The unit wakes up, takes readings, stores them in memory, and then periodically we'll push that data to a central database. You're able to view it on what's called FlowLink Global. Having said that, we are working on some other stuff that is called FlowLink Cipher. Some of you may have seen that at WWTP, which is a very exciting new software offering that we will be providing shortly. And what that will allow you to do is now the data can be pushed up to the cloud, and you will have full capabilities of using some advanced software analysis tools to be able to do, again, INI calculations, comparison of site data, and just a number of different things. The beauty of that is that you would not have to own FlowLink Pro, but you would need the modem, but it will transmit the data up to the cloud, and you have no maintenance issues with your server. Your IT guys will be happy, and away you go. So stay tuned for that. That is, again, within weeks away, so we're close to that, and you're going to be, I think, very excited when you see what we have to offer on that. Now, I have been recently involved in some project where somebody has a non-ISCO modem in there. And can we work with non-ISCO modems? Yeah, we will put out a Modbus output, or we can put out an analog output to hook up to somebody else's devices if they have that already. So a lot of capabilities there with the communications, and that'll be coming down the road. Okay, does the 0 to 10 foot mean the maximum water depth can be used is 10 feet? Yes and no. If you put it, the maximum distance from the minimum water is 10 feet. But if I have a 10-foot deep channel and my water level goes up 10 feet, you technically have overall 20 feet. So you could tell the meter your level is 10 feet, but it is only going to measure, if that water level goes down from 20 feet to 9 feet, it's not going to probably see that last 1 foot. So yes, it can be used in that. It will not work in a 20-foot deep channel that has no water and that you're going to be blind for that first 10 feet. Okay, how accurate is a laser in industrial flow if that flow has immediate discharging of rags? It will read the speed probably of the rags, depending on how fast those are moving. It has no idea that those are rags or those are water particles or particles in the water. So it just kind of depends on that. I will tell you, we have a lot more applications now using laser in industrial monitoring locations. And the reason is because most of the time they're either doing some sort of a batch discharge, maybe boiler blowdown, or it's when people go on break. So when you look at applications like that, the challenge is if I put in to capture low flow, I might have to put in a small flume. If I put in a small throat flume, there's a good chance I'm going to plug up. That isn't desirable. So the nice thing is you can put a laser in, and you can have you can put the laser in, not have to have a flume in there. You can pull the flume out. We have a lot of lasers comparing that they're verifying their flumes are accurate or not. And I can tell you we're seeing a lot of flumes that are not accurate, although they've been in for years and years. But now they're verifying, okay, this may not be the best method for measuring, and they'll pull the flume out. New applications, they'll put a metering manhole in, but they won't put a flume in that. They'll just have a nice straight pipe through there. We do have some installations in India where they have a discharge of viscous fiber, and it's working well in that. So yeah, there's a lot of applications that we've learned that we can read in. The beauty of the laser is you can lease one if you want, put it in, and we can verify and look at data with you and go, yeah, this is working, or no, this is not. So we're able to help you. Okay, max cable length distance on an EX, good question. The maximum cable length to the barrier, so this is from a barrier to the laser in the environment, hazardous environment, is 108 feet. From that point, your barrier has to be out of the area, and then from there we can run it several hundred feet to the electronics. But the maximum distance on the EX is going to be 108 feet. The standard laser is 180 feet, 180. So a little bit of a difference in the overall cable length. Can I do battery back with the 2160? The answer to that is yes. So on a 2160, and I have actually applications right now where people are using the 2160, which is the blue box area velocity or laser module. They have alkaline lantern batteries that they're using to power that. Down the road, they are planning on running AC power off to the side of the road. They want to continue to use that same system. They're saying, do we need to go signature? And the answer is no, you don't have to go signature. You can take that 2160, you can put it in your cabinet, and there's a small AC to DC converter that'll power that unit remotely. So now if you're doing cellular modems, you don't need a local display. You don't really have to change it out to a signature. You can leave it just the way it is and have that. Now the battery backup part, which is pretty cool about that, is you already have a battery system because you're running it portably in the manhole. You can take that same battery system and leave it on with two batteries in it, and you can run the power up through the bottom, which is a AC to DC 12-volt conversion. It will use that power, and if you lose power, AC to DC power, it will automatically switch to the batteries in there. So really a lot of flexibility on that. If you decided you wanted to switch from a in the pipe or in the manhole 2160 to a signature, let's say you want to move it out and you want to get it where you can read it, somebody wants to go by and be able to download using a thumb drive, it's the same exact laser sensor. So there's a small difference in the connectors, but that's very achievable as well. And so you could just easily swap it out and go, you know what, I want this 2160 to move to another bad location. It's in the middle of the manhole deal, and you rewire it and plumb it into your laser signature meter off to the side of the road. And I think that's about all the questions we have, but I appreciate all the questions. Please feel free to send anything you have to me. You can send those to rick.dey@teledyne.com or Darrell, DARRELL .kuta, KUTA, @teledyne.com as well. And we'd be happy to help you and answer any questions we can. And again, feel free to give us a call, but we appreciate you attending the webinar today. And stay tuned for more in the not too distant future. We have some exciting stuff coming out. So once again, thank you, and hope you have a great day.
Thank you for attending How to Measure Flow in Hazardous Locations webinar, and thank you to Rick for presenting on this topic. As mentioned, it was recorded and a video will be made available. If you have any questions and you didn't get Rick or Darrell's email addresses, feel free to reach out to me through Zoom, and I will forward it to the appropriate person. Thanks again for joining us, and have a great rest of your day.